Good afternoon, everyone. My name is Zhang Yucheng, and I am from Nanchang University. Today, I am honored to present my research paper, LoopDelta. Data backup is a critical method for file protection. Backup workloads typically contain a significant amount of redundant data. Eliminating redundant data in backup systems can greatly reduce storage costs. Data deduplication and data compression are two commonly used data reduction techniques. Data deduplication removes duplicate chunks based on their fingerprints, storing only one physical unique chunk. A limitation of data deduplication is that it cannot remove redundancy among non-duplicate, but highly similar chunks. However, such redundancy can be removed by data compression. Due to the complementary effect of data reduction, backup systems can use both deduplication and data compression to eliminate redundant data. Adding data compression to deduplication system faces four challenges. The first challenge is a low compression ratio because existing sketch indexing approaches either suffers from the low similarity between many detected similar chunks or miss some potential similar chunks. The second challenge is low backup throughput stemming from additional IOs for reading base chunks on the write path. The third challenge is low restore performance resulting from additional IOs for reading base chunks on the read path. The final challenge is the potential to miss similar chunks when rewriting techniques are applied. Before discussing the first challenge, let's talk about redundancy locality. In backup workloads, redundancy locality refers to the repeating patterns of redundant data among consecutive backups. The pattern that exists before deduplication is known as logic locality, and it is preserved in the recipe and the sequence of consecutive data chunks before deduplication. After deduplication, the pattern is referred to as physical locality, and it is preserved in container. We provide an example to illustrate logic locality and physical locality. This figure shows two backups, and before being written into containers, the duplicate chunks A, B, and D, appear in the same order in their respective backups. This phenomenon is known as logic locality. After the two backups are written into containers, the relative position of duplicate chunks in container 1 remain unchanged, and this phenomenon is known as physical locality. Which similar chunks are detected as base chunks for data compression depends on the adopted sketch indexing techniques. Existing sketch indexing techniques can be divided into three categories: logic locality-based indexing, physical locality-based indexing, and full indexing. Logic locality-based indexing techniques index sketches of the data chunks of the last backup. Physical locality-based indexing techniques index sketches of the data chunks stored along with duplicate chunks. And the full indexing technique indexes sketches of all data chunks in the backup storage. Next, we will introduce these three categories one by one. The first category is logic locality-based indexing techniques. A disadvantage of this category of techniques is that they may miss potential similar chunks existing across backup versions. We provide an example to show how this problem may arise. Let's assume that the first two chunks in backup 3 inherit from backup 1, where the rest two chunks inherit from backup 2. And B apostrophe is similar to B in backup 1. When detecting similar chunks for chunks in backup 3, B in backup 1 cannot be detected as a similar chunk of B apostrophe because its sketch will not be indexed. An advantage of this indexing technique is the high similarity of base chunks. This is because base chunks for data compressing a chunk is often its previous copy in the last backup. The second category is physical locality-based sketch indexing techniques that index sketches of the data chunks stored alongside the duplicate chunks. A drawback of this category of techniques is that they may detect self-referenced similar chunks as base chunks. Self-referenced similar chunks refers to similar chunks that appear within the same backup. Compared to similar chunks detected from previous backups, self-referenced similar chunks tend to share less redundant data with unique chunks of the ongoing backup. This is because the unique chunks of the ongoing backup are more likely to result from the similar chunks in the previous backups after undergoing slight modification. We provide an example to illustrate how this problem may arise. Backup N includes 8 data chunks, with chunk A appearing twice. B1, C1, and D1 are similar to B2, C2, and D2 respectively, so they are considered self-referenced similar chunks. The first 4 data chunks are stored in container X. When deduplicating the second A, the system will select container X for deduplication because of a previous copy of chunk A. Then the sketches of data chunks in container X are indexed, and B1, C1, and D1 are detected as base chunk for data compression of B2, C2, and D2. An advantage of this category of techniques is that it can detect most similar chunks, including those missed by logical locality-based indexing techniques, as long as they are stored alongside the duplicates in the same container. The final category is the full sketch indexing technique. This technique also detects self-referenced similar chunks as base chunks, similar to the problem faced by the physical locality-based sketch indexing techniques. An advantage of this technique is that it can detect all potential similar chunks, making it a useful upper bound for compression evaluations. Logic locality and physical locality have complementary capability for detecting similar chunks. Based on this, we propose dual locality-based sketch indexing to detect similar chunks by leveraging both logic and physical locality. Our approach indexes chunks of the last backup to capture highly similar chunks by leveraging logic locality, and indexes chunks in the container that hold the above-mentioned chunks to capture similar chunks stored in these containers by exploiting physical locality. The second challenge of adding data compression to deduplication systems is low backup throughput caused by extra IOs for reading base chunks during backup. In a typical deduplication-based backup system, prefetching metadata from containers being deduplicated against is a routine operation to accelerate duplicate detection. Due to redundancy locality, containers that hold potential similar chunks detected by our proposed dual locality-based sketch indexing would be accessed during deduplication. Based on this observation, we proposed locality-aware prefetching to avoid extra IOs for reading base chunks and improve backup throughput. For containers holding potential similar chunks, when they are accessed during deduplication to prefetch metadata, data chunks are also prefetched, namely piggybacked on the retrieval of the metadata to serve as potential base chunks. The third challenge of adding data compression to deduplication systems is low restore performance due to extra IOs for reading base chunks during restore. Our proposed locality-aware prefetching not only eliminates extra IOs during backup, but also reduce extra I/O during restore. However, when data chunks refers to data in the system, the base chunks of these data may still require additional I/Os during restore and decrease restore performance. Data chunks that refers to data whose base chunks require additional read operations during restore are referred to as base fragmented chunks. This is an example of a base fragmented chunk. 4 chunks in backup 1 are stored in container 1. C past feed in backup 2 are similar to C in backup 1, and theirs is data compressed and stored in container 2. C past feed in backup 3 refers to a delta, and the base chunk of the delta in container 1 requires an additional read operation during restore. Thus, this chunk is considered a base fragmented chunk. However, identifying such a chunk is a challenge because obtaining the container ID of the base chunk of a delta in the system is difficult. Storing containers IDs of base chunks along with deltas in container is vulnerable to garbage collection because base chunks can move around due to garbage collection. Storing fingerprints of base chunks and obtaining their container IDs through the fingerprints index may result in a large number of extra I/O operations. We propose cache-aware filter to identify base fragmented chunks with the assistance of recently prefetched metadata during deduplication. Identified base fragmented chunks are rewritten to avoid I/Os for base chunks during restore to improve restore performance. The rewriting techniques declare infrequently reused containers, which should not share redundant data with the current backup to alleviate chunk fragmentation. However, since base chunks are needed during restore, similar chunks in infrequently reused containers cannot be used as base chunks. Otherwise, the efficiency of the rewriting techniques would be reduced. In fact, data compression can be viewed as a two-step process. The first step involves generating a dirt for the target chunk, resulting two versions of the target chunk, an encoded dirt and an unencoded version. The second step involves removing the unencoded target chunk and storing the dirt to achieve a data reduction. When applied to backup systems, the target chunk refers to a chunk being backed up, where the similar chunk refers to a chunk in the backup storage. In order to leverage the benefits of similar chunks in infrequently reused containers, we propose the inverse data compression. Unlike the traditional data compression approach that encodes the chunk being backed up relative to a detected similar chunk in the backup storage, inverse data compression encodes the detected similar chunk in the backup storage relative to the chunk being backed up and generates a dirt. The dirt is then stored along with the chunk being backed up, resulting in two versions of detected similar chunks, an encoded dirt and an unencoded version. During the next garbage collection, the unencoded version is removed to achieve data reduction. We provide an example of inverse data compression. This figure shows two backups. 8 chunks from backup 1 are stored in containers 1 and 2 when the backup completes. Backup 2 includes 1, 2, 3, 4, 4 duplicate chunks and 1, 2, 3, 4, 4 unique chunks. When processing the backup 2, the container 2 is identified as an infrequently reused container because it contains only 1 duplicate chunks, the chunk F, where the container 1 is not an infrequently reused container. Because D2's base chunk is detected from container 1, we process it using direct data compression, which is the traditional approach. Therefore, the E2 and the G2, we process them using the inverse data compression. When the backup true completes, there are two versions of E and G, and the unencoded version in container 2 will be removed during the next garbage collection, thus achieving data reduction. We propose LoopDelta as a solution to embed data compression in deduplication-based backup systems to achieve a high compression ratio, high backup throughput, and high restore performance. We employ the 4 techniques mentioned above to address the challenges introduced by data compression. They are dual locality-based sketch indexing, locality-aware prefetching, cache-aware filter, and inverse data compression. 4 datasets are used for performance evaluation, including database snapshots (RDB), website snapshots (WEB), an open source code project (CHM), and a synthetic dataset (SYN). Multi-version inheritance is common in RDB and SYN datasets, and the web dataset contains substantial self-referenced duplicates and self-referenced similar chunks. This figure illustrates the percentage of detected similar chunks of existing sketch indexing techniques and our proposed LoopDelta on the 4 datasets. It is obvious that our approach can detect almost all potential similar chunks and identifies more similar chunks compared to the logical locality-based technique. We use average data compression efficiency to measure the similarity of detected similar chunks. We call it DCE for short. A higher value of DCE indicates a higher level of similarity. This figure indicates that our approach achieves a higher DCE than the other approaches on the web dataset. This dataset contains a significant amount of self-referenced similar chunks. Where on the RDB dataset, our approach also achieves a higher DCE than the physical locality-based indexing technique and the full index technique, but a lower DCE than the logical locality-based indexing technique. This table presents the improvements in restore performance achieved by cache-aware filter when rewriting technique is applied. The results suggest that cache-aware filter improves restore performance by 11.7% to 15.6%. This figure illustrates the proportion of the compression ratio achieved by direct and inverse data compression on the 4 datasets. The results indicate that the compression ratio achieved by inverse data compression accounts for up to 16.4% of the compression ratio achieved by both direct and inverse data compression on the 4 datasets. This figure illustrates the compression ratio achieved by 5 data reduction approaches on the 4 datasets, including 3 existing approaches, MAGA, SIDC, and Greedy, and 2 versions of LoopDelta, one without rewriting called LoopDelta, and one with rewriting called LoopDelta-cap. The applied rewriting scheme is capping. The results indicate that LoopDelta achieves a compression ratio comparable to SIDC and Greedy, and higher than MAGA on RDB, CHRO, and SYN datasets, while achieving the highest compression ratio on the web dataset. This is because this dataset contains substantial self-referenced similar chunks. Additionally, on the RDB dataset, rewriting improves the compression ratio because it allows the most recently related chunks to serve as a base chunk. For previously related chunks, the similarity between the most recent related chunks and the chunk in the current backup is higher. However, on the other datasets, rewriting slightly decreased the compression ratio. This figure illustrates the restore performance achieved by the 4 data reduction approaches, and the results indicate that our approach achieves higher restore performance than the other approaches, and rewriting further significantly improves the restore performance on top of our approach. This figure illustrates the backup throughput achieved by the 4 data reduction approaches. The results indicate that our approach LoopDelta achieves higher backup throughput compared to the other 2 approaches, and rewriting further significantly improves the backup throughput on top of LoopDelta. Thank you for your attention.